Oh, hello. Today's episode of Garage Science has to deal with not the drill press, not well, Bob's included, but actually this, the electric motor. Where did it come from? And what principle makes it work? We're going to start with the history, the discovery of what makes it work. All right, Bob, let's set that up. That tiny discovery that a current-carrying wire can affect the compass may seem like a rather minimal, tiny little discovery, but the implications, the applications of that discovery never stopped once that discovery was made, and it's still going strong today, probably more today than ever. And that concept is pervasive in our lives, though we might not think about it all the time. So what really was this discovery? Well, let's take a look. A gentleman noticed if you put a current-carrying wire near a compass, like this is 1.5 volts, the needle moves. Now, that doesn't seem like much, like I said before, but that is amazing. So, being a scientist, he said, well, what if? What if you put more current through the wire? So we've got 3 volts. Well, probably an 8th grader at the time said, hey, just give it all of it. So there's 9 volts. Look at that. It goes even farther. Now, if you notice, each time the needle on our compass swung to the left. Well, what if we have the current going the opposite direction? Will that affect it? That's a legitimate hypothesis. Let's give it a whirl. There you go. The current's going the opposite direction. The needle goes the other direction. So what's really happening here? We must be producing a second magnetic field, because we know if you take a magnet has a magnetic field and that affects it. So obviously there must be a magnetic field being produced around our wire, and that is true. Let's experiment even more, because that first discovery was about 1820. Another gentleman came along and he did this. He started to wrap the wire. What if you wrap the wire in a coil? That's called a solenoid. We're going to put that on there. I connected it to a switch so I'm not killing all the batteries all the time. Come on, compass, get in there. We got to learn today. Okay, close the switch. Look at that. Look at that needle movement. Yeah. Well, if 5 is good, well, then 20 must be better. Do you ever notice how wires take on a life of their own when you try to use them in a hurry? Okay, here we go. Same compass, same amount of electricity, because in experiments you keep things the same. We're going to close this. Bam! Did you see that? Look at that, look at that. Come on, Bob. Bam! Look at that. That is amazing. You can get hurt by that. So, we've discovered what? That coils don't really make more magnetic field. What they do is they concentrate. They bring it together. So a solenoid will do that. Well, what if you add things to that solenoid? What if you add things to that? I'm going to tape this down because these wires have been balking all day. Okay, now I need a shorter wire here. Bob, can you hand me another wire, please? Really, Bob? Really? Have you been taking your meds, Bob? I mean, I'm not judging. Not judging here. I'm just thinking that that's probably pretty sick on a lot of levels, Bob. Could have been a relative, Bob. Think about that. All right, moving right along. All right, so we have our solenoid, and right now we're just going to try it hollow, see what happens. Close the switch. Ha! Look at that needle deflecting. See that? Look at that movement. Woohoo! Well, let's try this. Here's a black plastic rod. Let's try that in the middle of it. Whizzle that little thing right in there. And closed. Whoa. Yeah, what do you think, Bob? Exact same amount. Rinky-dink little amount. But it did move. Okay, it did move. That's important to remember. It did move. Here's a glass rod. Surprised we haven't broken that one yet. And close, same little teeny weeny, itsy bitsy little movement. Okay. Let's try, we have this iron bar sitting around. Let's try that one. I can only go so fast. There we go. All right. And try that. Whoa. Okay. And closed. Woohoo! So, for somehow, it appears that iron, maybe all metals, concentrate the effect of the magnetic field. Well, let's try a different metal. Let's try this brass rod. Let's try that. And closed. Nothing. Could be the marshmallow Easter chicken. You never know. All right. No. So what did we discover here? A solenoid does concentrate it. And it appears that not all metals, but iron, really concentrates it too. So we found out that around a wire is a magnetic field. We can concentrate the magnetic field. And if you put an iron bar in the middle of your wrapped up wire, your solenoid, you can even concentrate it even more. So let's go off and look at some machines that use this concept to help us out. All right, Bob, let's go check something. I'll tell you what, I'll set them up. You go check to see if you took your meds today. What we're studying on this episode is electromagnetism. Now, in the beginning, there was electricity and there was magnetism, but until Ørsted made his discovery, there was no electromagnetism. It was suspected, it was hypothesized, it was theorized that the two went together, but nobody knew how until Ørsted made this discovery. And this is an Ørsted's law apparatus. And I'm just going to show you here quickly. There's the compass needle, there's our current carrying conductor. And if I just touch this to this, you can see there the current going through that thick, heavy wire there makes a magnetic field that affects the needle, the compass needle. And that's what he discovered. That was his big discovery. And he used that device to show his peers. Current carrying wire has a magnetic field around the outside of it. Now the second part of this was discovered by Andre Ampere. Now, his name is what we use to measure the amount of current going through a wire. He discovered the solenoid. If you wrap that wire up, you concentrate the effect of the magnetic field around it. And if you put an iron bar in there, you get much more concentration of that magnetic field. So that produced the first electromagnets. So let's go take a look at the application of electromagnets. Thank you, Bob. The first device that Bob and I want to show you that uses Ørsted's principle is the electric bell. It works this way. You have a source of power down here. Wire goes up like that, goes into these two coils of wire, these two solenoids, which turn into electromagnets. They will then pull this bar over, which makes the hammer strike the bell. But it also breaks the contact right here, so the circuit's broken, so the spring pulls it back, and the whole system starts over again. Let's take a look at the inside of this thing, so you can see what an actual one looks like. There it is. You can see that right there is your electromagnets. There is the points. When the clapper comes over, it breaks the points and it stops being a circuit. So the spring brings it back. That's how that works. It uses electromagnets. Now let's just show you how it runs. Hook this wire into here. Hook this wire into here. And you can see it working. See a little spark in there? See a little blue spark? That's it. That's really annoying, isn't it, Bob? That is really annoying. So, 3 of them would be really annoying. What do you think about that, Bob? That's about as annoying as a lab partner who doesn't take his meds. All right, let's go off to another machine. Okay, Bob and I talked. I apologized. I'm even going to show him that I care so much that I got him a pepperoni stick. Nothing says friendship like that. Okay, Bob, let's talk about the speaker here. The speaker is actually a cone speaker, and it shows Ørsted's law in action again. Here's your permanent magnets. The permanent magnets are on the bottom of the speaker. See? Permanent magnet. And then electricity runs in to a solenoid inside on the bottom of that cone. And that's a free-floating thing. But if you run electricity through that, as you know, put electricity through it, you're going to make a magnetic field, a second magnetic field to interact with the permanent magnet's magnetic field. Sometimes electricity will be repelled. This magnetic field will be repelled by the north. Sometimes it'll reverse it and it'll be attracted to that. So this will go back and forth. And I can show you that. Okay, that might be a little difficult to see, so hold on a second. We have a slightly bigger one we can show you. If you watch this. See that? You can see it. It's all produced by Ørsted's law. Two magnetic fields, electricity going through a conductor, producing a magnetic field, and we're having it react to another magnetic field that's already there. So you get motion. There you go. Thank you, Bob. All right, let's go look at another device. Bob and I are using this device that works with Ørsted's principle to communicate, because Bob he was just too cold. So he said he needed to go in the house, and he's down in the basement working, so he's been sending me a message through this. Let me show you how this works. I asked him to stop so I could show you how this works. You can see here are two large solenoids connected to a battery, and that's connected to wires that go down to the basement. When he hits the button, it pulls this bar down, makes this magnets. They pull the bar down, it makes that clicking sound you're used to hearing with a telegraph. He should be sending the rest of the message anytime soon. Look, he can't spell very well. He spelled duck instead of duct. I know he wants duct tape. Oh, okay. Wait a minute. Send more duck sauce? What's he need? Oh, Bob called out for Chinese again. Bob, we're not supposed to do that. All right. Bob and I have come outside here to show you another thing that works with electromagnetism. This is an electromagnet. It's got a D-cell battery there and lots of wraps of wire in there. A really big solenoid. And if we take and put this on here, and then I connect this wire, that'll connect the circuit. And we have this nice electromagnet here. Put this bucket on here. And we have Bob's bowling ball. It's not bowling at the moment, so we're going to put that on there. Scared me. And we got Bob. We're going to put Bob in there with this bowling ball. And now, that's being held up by one D-size battery. So if I disconnect that wire, that stops the circuit, stops the magnetic field, and yeah, okay, so let's try this. And it's on. Whoa, that's going to leave a mark. Maybe you want to take a little time out there, Bob. Just rest a little bit. The device that Bob is taking his little timeout nap on is called a galvanometer. It's a very super sensitive device. The way a galvanometer works and how it has to do with Ørsted and Ampere's principles is this. Inside there is a permanent magnet. You can see the donut-shaped permanent magnet there. And inside of that is a solenoid, wires wrapped around an iron core. You can see it in there, and you can see it right here in the diagram. And when electricity passes through those wires, it produces a second magnetic field that is either attracted or repelled by the permanent magnet, and that makes the needle move. There's a little spring in there that brings it back to center. Any meter you see like this has one of them in it. And as a matter of fact, I took the back off of this one. I'm going to take the front off of it also so you can see inside of it and actually see the pieces. Here, I'll get this a little closer so we can see it. There you go. You can see in there, there is the solenoid. See the wires? There's a solid piece of iron there, and that's connected to the wires. And as that magnetic field there interacts with the other magnetic field of the one that's already in the back there, and so the needle will move. I'll lightly move it, and you can see how the thing moves back and forth. A spring brings it back. That's how it works. That's a galvanometer. Thanks for your help, Bob. The last device Bob and I want to show you for this episode is the electric motor. Now, electric motors are ubiquitous. They're everywhere. There's probably not a room in your house that doesn't have an electric motor of some sort. Tiny, large, whatever. It's got a few basic parts. This is why we're showing it with Orsted's, because here you have one permanent magnet, and then you have a magnet that has to change. But that magnet, so there's two magnetic fields. The interplay of those is what gives us motion. In the meter, you saw a motion that would just go like this. Well, we've got this to go continually around. Once they discovered how to make a commutator and brushes, we were off to the races, so to speak. As this turns, as you notice, the south is attracted to the north, north to the south. As it turns, it has to change here. And that's the job of the commutator. It'll change, and then these are repelled instead of attracted like they are there. This is another diagram. In this, you can see, this just happens to be from a book from 1957. It was a good year. Here are your permanent magnets. Okay, that's one set of magnetic fields. Here is your other one. This is a solenoid. And how does the electricity get there? Well, the electricity comes in. Here's your electricity going in. One goes into this magnet. The other one goes up here, goes in the brush. The brush touches this side of the commutator. So that sends the electricity in here. Goes the whole way through, over to here, back out, back again. And as soon as this thing turns, the brushes stay still. But those two half moon-shaped things, this one will now touch this, and this will touch there. So the electricity goes backwards, and it switches the magnetic poles. So every half of turn, the commutator allows the electricity to switch and go the other direction. Now here's a rather large electric motor. That's from his toothbrush. I'll show you the parts in here, and then we'll go look at some other ones. See if I can get this lined up for you. There you go. Here are your field magnets. In there you can see the commutator. Here are the brushes right here. If I turn that, you can actually see the armature in there moving. Maybe you can. Maybe, there you go. See the armature moving in there? That's connected to the shaft. That's the part of the motor that moves. Okay, there you go. Let's go look at some other ones. Before we show you the actual motors, Bob and I wanted to make sure with this demonstration, it's pretty small, pretty simple, be fast. You want to make sure you keep your light of learning on to understand this important part of the motor. It's very simple, but it can be tricky. You have your field magnets. That's the one magnetic field. And inside that field is the armature. Armature, got it? Armature. Now, that is an electromagnet that's free to spin. And what happens is, it's down like this. Okay, it's like this. And it goes, this one's attracted to there, this is attracted to there, and it goes ding, 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 ding. Unless, when it gets to here, the momentum takes it by a little bit, and then the electricity, because of the commutator, changes the direction of the electricity, so the armature's magnetic field is reversed. And so now they're being repelled and attracted to the other end, and when it gets here, it flips again. Every half turn, it switches polarity. Every half turn. And that is why it continues to spin. It's hard to imagine as that thing's spinning as fast as they are. When you watch them when they're spinning, 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 every half turn, they switch polarity because of the commutator making the armature switch polarity. There you go. Now let's go get to those motors. Well, Bob and I thought we'd show you a couple of working motors here. Here's one. you can actually see the field magnets. They're bar magnets. There's your commutator. There's your armature going around. And there's the brushes bouncing back and forth. You can actually see the sparks in there. There's some other ones here too. This one is one that Bob and I built. We just hand built this thing. Put that in there like that. Give it a little twirl. And there you go. A working electric motor. See? There's your field magnet. There's your armature. And we've taken half of the insulation off the wires at both ends. So the electricity goes in one, out the other one, works. Here's a much smaller version of that. It just has a D-sized battery inside of it. Made a coil of wire. Took the insulation off this end, stuck that on there. Like that. Give it a little twirl. And it's quite happy that way. Okay. They all have the basic same parts. This is called a St. Louis motor. This one right here is called a St. Louis motor. We'll plug this one in. Give it a little oomph-de-doo. And there it goes. Okay. You can see here, here's your field magnets. It's all have the same parts. Field magnet. There's your commutator. There's the brushes. And you can see the armature flying around in there. Same basic parts. Here's one we built out of a horseshoe magnet a long time ago. Here you can see before we started up, there's your armature. That is so old that it's actually wrapped in cloth. That's the armature. There's your field magnet. Here's your commutator. There you go. See? Isn't that amazing? We have one more to show you. I'll move that one away a little bit. This one is one of our newer ones. This one actually has, you can see the field magnets in there. Mr. Net, don't make a mess of it. You can see the field magnets down here. Make these things magnets. There's your armature. This one comes with 3 different armatures. You can have, yeah, that works real well. 2, 3, or 4. I'll just turn this on. Give it a little bit of a oomph. And there you go. They've all got basically the same parts. So don't be afraid of electric motors. You can look up designs to build these. They're fairly simple. As long as you can get some wire and a magnet, you're doing all right. Oh, this little guy quit. Well, don't you guys quit. What we want to see is, we want to make sure that you keep your line of learning on. And we'll see you next time on Garage Science. Have a motion-filled day.
Bye.